Okay, so I had seen some, somewhere, I don't remember, but so it is not my, idea, this sentence, but I thought it's nice. Okay, so in a surface, we will study basically two type of curves. One of them is called principal curves, the curves which goes in principal directions, and the other one will be geodesics, which kind of the curves which minimizes distance. Okay, so let me start with the definition. A regular curve alpha in a surface M in R3 is a principal curve, provided that the velocity alpha prime of alpha always points in a principal direction. Çok yaşa. Okay. Acaba sesim gidiyor mu? Gidiyormuş, tamam. Okay. Now we have a remark. So principal directions, remember, are the directions where the curvature is extreme, right? Along which the curvature changes in extreme way, either the lowest rate or maximum rate. So these curves follows those directions. So along these curves, the surface bends either in most extreme way or in the slowest way. Okay. So principal curves moves in directions in which the surface bends in extreme values. Okay. Through a non-oblique surface, non-oblique means at that point, right, normal curvatures are not constant. So it means there is a maximum, there is a minimum. And remember, there is a unique maximum or unique minimum. And those directions are orthogonal to each other, right? The principal directions are orthogonal to each other. If the point is oblique, then along all the directions, the normal curvature is the same. In that case, there is no maximum, there is no minimum. All the curvatures are the same. But if your surface is non-umbilic, it means at all points you have two directions, two principal directions. Therefore, your goes through along one of these directions. Through a non-umbilic surface, neglecting parametrizations, there are exactly two principal curves. Passing through every point. Which are orthogonal. Let's see, for example, a picture of such a surface. So this is an non-umbilic surface. Consider, for example, this point. Through this point, there are two principal directions. And actually, for any point on this curve, I guess this curve is one of the principal curves along which the curvature is positive and maximal in that sense. If I choose my normal vector u in this direction, then this curve has positive curvature because the normal direction of this curve is parallel to this one. Therefore, this is positively curved. And this one is negatively curved. So these are the principal curves. If you choose some other point, let's say this point, and here you see that these curves are, of course, perpendicular to each other at every point. Well, wherever they meet, of course. Through this point, what are the principal curvature? I mean, principal curves. I don't know what. Ya eğimin en fazla olduğu. So maybe something like this, right? If you find one of them, the one which is perpendicular to that one, I guess it should be something like this, right? And the other one, so along this, the curvature seems to be minimal, and so maybe something like this. This one is along which the curvature is changing in maximal way. Okay. Of course, on the other hand, at an umbilic point, every direction is principal. So, for example, consider sphere. If you choose any point here, any direction is principal, okay? Any direction is principal. So if you choose just any curve, its tangent direction will be always principal, right? Because every direction is principal. So if you take a sphere like this, any curve is principal, because if you choose just any curve, okay, its velocity vector is principal at all points, because every vector is principal. Therefore, every curve is principal, right? So on a sphere, every curve is principal. So it's not, you know, something interesting in that case. Infinitely many, yeah. Okay, we have a lemma. Let alpha be a regular curve in M on a surface M in R3. Regular means the tangent velocity vector is never zero. So speed is never zero. And let U be a unit normal field along alpha. Then we have the following statements. First one is this: the curve alpha is principal if and only if U prime and alpha prime are collinear at each point. So this is a vector field. You take its vector field along alpha. So you take its derivative with respect to t. You get another vector field along alpha. And you also look at the velocity vector of alpha and check whether they are collinear. Okay, so if they are parallel or not. The second statement is this: if alpha is a principal curve, then the principal curvature along alpha prime, curvature along alpha prime is alpha double prime dot u divided by the number alpha prime dot alpha prime. Okay, now here is the proof. But first, let me explain what is U prime. So suppose this is our surface, and I have this curve alpha t. So from an interval, I have, so this is interval I, let's say, here is t, mapped alpha t. And along this curve, I have a vector field, okay? Unit normal vector field. Unit normal vector field along alpha. It may be defined everywhere on the surface, but all I care is that it is defined on this curve. So it is something like this, okay? Şunu belki şöyle mi çizsek? So let's say it is this one. So this is just, so if this point is alpha t, this is just u of alpha t, okay? So it's a function of actually t, right? It's a function of t. It's a function of t. Therefore, I can talk about its derivative, okay? So u prime is the derivative of this expression. Okay, now let's see. Collinear means two vectors are parallel. Okay, collinear means they are parallel. Collinear. Collinear points means they lie on the same line, but here two vectors are collinear means they are parallel. Now here is the proof. Oh, I said already proof. Okay. First, we have a claim. Yeah, it means that. Right, we defined actually covariant derivative, right, as the derivative of this gadget, right? So well, actually that's our basically claim. As of this is what was this? Okay, so the claim is this, but you know, this is of course trivial, as you pointed out. So we know that SP of alpha prime by definition minus d dt. So this is minus the covariant derivative along alpha prime of u, right? But this is just, what was this? This is just d dt of u of alpha t. And this is what alpha u prime is. Okay. All right. Hence, so assuming this claim, I mean, we proved it, of course. So u prime and alpha prime are collinear if and only if S of alpha prime and alpha prime are collinear. But this is an operator. They are collinear means so S of alpha prime is just lambda times alpha prime. This is a non-zero vector. If two vectors are collinear, one of them can be written in terms of the other one, provided that it is not zero vector. Okay, so I can write it this way, but this means that alpha prime is an eigenvalue for this symmetric operator, right? And hence alpha prime is an eigenvalue for S, but eigenvalue means it's a principal direction. Eigenvector, yes. Hence, alpha prime is a principal direction. Tamam mı? Okay. And actually, it's vice versa, right? This is if and only if. So if it's a principal direction, then it's an eigenvector. So it satisfies this. Therefore, these are collinear. But if they are collinear, then these are collinear. Okay. Okay. For the second statement, if alpha is the principal curve, then of course alpha prime divided by its length is a unit vector along alpha prime. Therefore, it's a principal direction. Here, actually, I said principal direction, but actually, alpha prime doesn't have to be a unit vector. So technically, alpha prime is not a principal direction. It should be unit vector, but what I mean is it points in the principal direction. Maybe points in a principal direction. So it's, but this one is a principal direction, unit one. It is always a principal direction. Hence, right? Principal curve means its tangent vector always parallel to a principal direction. Therefore, if you divide it by its length, then you get a unit vector in a principal direction. So it means it's a principal vector or direction. Hence, if Ki is the principal curvature, to alpha, then this gadget right? Principal direction. So this is an eigenvector, and eigenvalue is the principal direction. So it is ki times alpha prime divided by this vector, since it's the eigenvector. Thus we have this ai. I can write it this way. So it is this is a vector, and that vector is just a number times a unit vector, right? This is a unit vector. How can you get this number? Well, I can just take that product with this unit vector, right? So I write it this way: S alpha prime divided by this, that product with alpha prime is just ki alpha prime, that product with alpha prime. Well, sorry, alpha prime, norm alpha prime. Here I also have norm alpha prime, so that, you know, this is unit vector. This thing is equal to 1. Therefore, ki is what? Ki is just this gadget product with alpha prime divided by norm alpha, which is just, okay, norm alpha prime. And since this is a linear operator, I can take 1 over alpha norm alpha prime outside. So I can write here alpha prime times 1 over norm alpha prime. But then that will mean I have square here. So it's ki equal to S of alpha prime dot product with alpha prime divided by alpha prime dot product with alpha prime. Okay? Tamam mı? So along principal curves, this expression, so if you have a principal curve, then this expression is the principal curvature. Of course, you know, principal curvature at alpha t, right? Principal curvature at alpha t. At any point, you are at some point. At that point, the principal curvature along which alpha travels can be computed like this: shape operator of alpha prime dot alpha prime divided by that gadget. All right. Here is another lemma. Let alpha be a curve cut from a surface by a plane, surface M in R3 by a plane. So we have a surface and we cut it by a plane. Yes. Yeah, yeah. Oh, I see. I didn't. Yeah, the statement was that. Yeah, okay. Yeah, I forgot to write the last line. Okay, I'm sorry. I'm sorry. Here we have this. This expression is just alpha double prime dot u, and then I have alpha prime, alpha prime. So this is better, of course, because you don't have to compute this gadget, right? Alpha double prime dot u divided by this. Sorry. Thank you. Okay. If the angle between M and P is constant along alpha, then alpha is a principal curve. So what does this mean? We have, let's say, a surface. We cut this surface by a plane so that at each point, the angle between the plane and the surface are the same. How can you measure the angle between two surfaces, intersecting surfaces? Well, you have to look at their normal vectors and the angle between the normal vectors, right? For two planes, if you have a plane like this, and let's say another plane, okay. How can you measure the angle between them? Well, the right way of measuring the angle is this. is the following. You look at the normal vector of each plane. For this horizontal plane, this is the normal vector. For this plane, the normal vector is what? Something like this, probably. And this is the angle between them. For arbitrary surfaces, how would you compute the angle between them? At the point of intersection, so let me try to okay. Suppose this is the intersection of the plane with the surface. What you do, you look at the normal vector of your surface at this point. Let's say, so it is pointing, since it is, it's pointing something like this, I guess, surface. And for the plane, the normal vector is something like this. Yok, bu pek olmadı, değil mi? Yani aslında yok, olabilir. Şöyle mi yapsak? Şimdi horizontal olsaydı okay, yeah, it should be something like this. So this angle. But you measure this angle at all the points of intersection curve. Okay? And we assume that that angle is constant. And the claim is that in that case, the curve is principal. Let's see. Let U and V be the unit normals to M and P respectively. So in this case, so this is my surface M, this is my plane P, and normal vector of the surface is U, normal vector of the plane is V. Okay? And this is the angle between them, and we assume that that is constant. Let's see. Well, if something is constant, you know what to do, right? Take its derivative and obtain 0. Right? This is a differential geometry course, so we just take derivatives. Okay. Let me tahta döndü değil mi? Hence U dot V, these are two unit vectors. So this is norm of U, norm of V times cosine of the angle between them. Let's say cosine theta. Theta is this angle. Let's say theta. Of course, as you move on this curve, you know, as time passes, both these vectors changes and the angle in general might change, but in our case, it doesn't change. So theta is a constant angle. Okay, so theta is this angle here. In general, it might change, but by assumption, it is constant. All right, so take ddt of both sides to get, well, U dot V. This is just, this is one cosine theta, but this is 0 because angle is constant. And what is this? This is just U prime dot V plus V dot U prime. Okay. Okay, here is okay, since oh, here, of course, the normal vector, this is not correct, right? U dot V prime. V prime is also 0. Why is that? It is the normal vector of the plane. Normal vector of the plane doesn't change, right? Normal vector of the plane is constant. This is also 0. Since V is a constant vector field because the normal vector of the plane doesn't change. V prime is also 0, so that U prime dot V is 0. Well, okay, since U is a unit field, right? We have U dot U is equal to 1, so that when you take derivative, taking derivative, we get U prime dot U plus U dot U prime is 0. So 2 times U prime times U is 0, meaning that U and U prime are perpendicular to each other. Okay. Well, here V is also perpendicular to each other. I mean, perpendicular to U prime. So we see the following. Hence, U prime is orthogonal to P, the surface, because bir dakika, U prime no. Efendim? Yok, bu 0 değil mi? Bu 0 olduğu için U prime V 0 oldu. Right, this is 0 because V prime is 0. Therefore, this is 0. This means V and U prime are perpendicular to each other. U and U prime are also perpendicular to each other. Hence, U prime is orthogonal to P and U. U prime is orthogonal to P. Well, that's not true. I mean, right? U prime is orthogonal to this vector, therefore in the plane P. Şöyle, orada bir gariplik var. Şöyle diyeyim. Okay. Alpha prime and U prime are in the same direction. Why is that? Alpha prime is the curve of intersection, right? Alpha prime is this. This vector lies in both tangent spaces, right? So alpha prime lies in both tangent spaces. Therefore, alpha prime is perpendicular to U and alpha prime is perpendicular to V. U prime is perpendicular to U and U prime is perpendicular to V. So, and
yayın gitti de.
Durdu mu? Tamam. Özür dilerim.
Teşekkür ederim.
Haha, bir şey değil. So let me explain again. This is the curve of intersection. Its tangent vector is perpendicular to both surfaces of intersection. Why is that? Because this tangent vector lies in the tangent space of the surface and the plane. Therefore, it is perpendicular to both normal vectors of the surface and the plane. But on the other hand, U prime is perpendicular to U, and U prime is perpendicular to V. Therefore, this U prime should be parallel to alpha prime. Okay? So let me write that down. I have two vectors. U and V, and I have two other vectors which are perpendicular to both of them. It means they are perpendicular to the plane generated by these two vectors, but there are only one direction, right? Which is normal to both of them. It is either this one or this one. So U prime and alpha prime are like this, or they point the same direction. In any case, I mean, so alpha prime and U prime are parallel to each other. Are collinear. Hence, by the previous lemma, alpha is principal. And this finishes the proof. Okay, yeah. So you mean if you have a principal curve that is obtained by I'm not sure. I mean, you have to build up the plane. I mean, yeah, I am not sure. I'm not sure if every principal curve is obtained that way. I mean, if you can find a plane which is perpendicular, which cuts the plane at a constant angle at all points, I'm not sure. Well, for example, consider the sphere. Every curve is principal, but every curve is not obtained by cutting it with a plane. Here, of course, this argument, as I pictured here, assumes that U and V are linearly independent. Note that this argument works only if U and V are linearly independent. So we have to consider the case where, you know, if they are linearly dependent. If U and V are linearly dependent, then Of course, U is plus minus V because they are two vectors. They are linearly independent. Dependent means one of them is a multiple of the other one, but they have both length 1. Therefore, they are either equal or one of them is the negative of the other one. But in this case, however, V prime is 0, so that this is the normal to the surface, and it is 0. Its derivative is 0 because it's a constant vector field. Therefore, U prime is 0. So that alpha is clearly principal in this case. Why is that? If U prime is 0, okay. why is that? Yeah, I think it obeys the definition. Okay, let me think about it and tell you in the second hour. All right, let's stop. Yok. Kaydı durduracağız.